So the next topic that we present in chapter 4 is indirect argument, which includes contradiction and contraposition. So we first explain proof by contradiction. That's a very popular method for proving a statement. Basically, in the first step of this method, we suppose that the statement that is provided is false. It means that we suppose that the negation of that statement is true. Then in the second step, we show that this supposition leads logically to a contradiction, and from these first two steps we conclude that the statement is true. So let's see an example. For example, we want to prove that there is no greatest integer. Okay, we want to use the method of proof by contradiction to show that there is no greatest integer. To prove this, we need to assume or suppose that the negation of this statement is true. It means that we need to prove that there is a greatest integer. Let's assume that that greatest integer is n. Okay, so we assume that that greatest integer is n. So the capital N. So the capital N should be greater than or equal to n for all the integer. Why? Because capital N is the greatest integer, right? So it should be greater than all other integers. But if you consider m equal to capital N plus 1, then based on the fact that we know that some integers are closed under summation, n plus 1 is also another integer. So m, which is equal to n plus 1, is also another integer, but we know that m is greater than n because m is equal to n plus 1. So in one side we know that m is greater than n. Also we know that n is greater than all other integers. So this will reach us to contradiction, because on one hand we know that n is greater than or equal to m, and on the other hand we know that m is greater than n. So it's impossible that we have both directions of an inequality at the same time. So we reach to contradiction. As a result, we can say that we have proved that there is no greatest integer. Okay, so the next example of proof by contradiction is theorem 4.6.2, which basically says there is no integer that is both even and odd. Let's see how can we prove it using the method of proof by contradiction. So to prove it by contradiction, as another example of proof by method of contradiction, consider theorem 4.6.2, which basically says there is no integer that is both even and odd. So to prove it by method of contradiction, we have to assume that there is an integer that is both even and odd. Okay, so let's assume that that integer is n. So based on the definition of even number, n is equal to 2a for some integer a, and also since n is both even and odd, n is also odd, so n can be written as 2b plus 1 for some other integer b, and as a result n is equal to both 2a and 2b plus 1, so 2a is equal to 2b plus 1, right? And if you do some basic algebra, you see that 2a minus 2b is equal to 1, and then by factoring it 2, you have 2 times a minus b is 1, and so finally you find a minus b equal to 1 over 2, right? So we know that 1 over 2 is not integer, but since a and b are both integers and integers are closed under subtraction, so this the left side of this equation is an integer and the right side is not an integer, so it's impossible that an integer is equal to a non-integer, right? So we reached a contradiction. That's why we can claim that we have proved theorem 4.6.2. Okay, so another example 4.6.3. Let's prove that the sum of a rational number and an irrational number is irrational. To prove this, we need to suppose that its negation is true. It means that we need to suppose that the sum of a rational number and an irrational number is rational. Okay, so let's assume that the rational number that we are talking about is called R and the irrational number is S. Okay, so numbers R and S are respectively rational and irrational, and since we suppose that it's the negation of this statement is true, so R plus S should be rational, right? Because the actual statement is the sum of rational and irrational numbers is irrational, right? So since we are proving by the method of contradiction, we have to assume that R plus S is rational. Okay, so we have R is rational, so R can be written as A divided by B based on the definition of rational numbers, and B is obviously not 0 because it's in the denominator, and also since R plus S is rational, it can also be written as C plus D, where D is not 0, right? So if you substitute these two equations, if you substitute the first this equation into this equation, we can get A over B plus S is equal to C over D. Okay, so instead of R, I put A over B, and if you subtract A over B from both sides of this equation, what you get is this. You get S equal to BC minus AD divided by BD, right? And then since A, B, C, and D are all integers, so denominator of this fraction is obviously an integer, and the denominator, which is BD, is also integer, and since B and D are not 0 based on the property of zero product, we can conclude that BD is also not 0. So based on the definition of rational numbers, we can conclude that BC minus AD divided by BD, which is equal to S, is a rational number, right? So this contradicts with the first, assumptions that we had. We said S is irrational, right? But here we prove that S is rational. So a number cannot be both rational and irrational. That's why we have reached contradiction, and as a result we are done with the proof of example 4.6.3. After introducing the method of proof by contradiction and seeing a few examples, let's see a very similar method which is called the method of proof by contraposition. Okay, so this method is used when you want to prove a universal conditional statement like this. Let's assume that for every x belongs to D, if P of x is true, then Q of x. Okay, in order to prove this, we basically prove it's contrapositive. So we say for every x belongs to D, if Q of x is false, then P of x is false. Okay, to do this, we need to suppose x as a particular but arbitrarily chosen element of D, and we should assume that x of D, Q of x is false, right? And then after assuming that x is such an element which belongs to D and Q of x is false, we need to prove that P of x is also false. So these are the steps of a method of proof by contraposition. So in the first step, we need to convert that statement into its contrapositive, and in the second step, we basically need to prove the contrapositive by supposing an arbitrarily chosen x belongs to D that makes Q of x false, and proving that P of x is also false. So let's see proposition 4.6.4, which basically says for all integers n, if n squared is even, then n is also even. Let's assume that we want to prove this using contraposition. Okay, so if I want to prove it by contraposition, I have to first know what is what the contrapositive of this statement is. So the contrapositive becomes for every integer n, if n is odd, then n squared is odd, right? So we first assume that we have an integer like n and n is odd, and then we prove that n squared is also odd. So let's assume that we have an integer n which is odd, right? So n, based on the definition of odd numbers, is equal to 2k plus 1, okay, for some integer k. Now, by substitution and algebra, we can say that n squared is also equal to, instead of n, I put 2k plus 1, which is 2k plus 1 squared. And if you do a basic algebra, you'll get 4k squared plus 4k plus 1. And if you put 1 aside, you can factor 2 from the other two elements of this summation. So it's going to be 2 times 2k squared plus 2k plus 1, right? But as we know, integers are closed under multiplications and summations, so 2k squared plus 2 is a new integer, right? So we basically prove that n squared is equal to 2 times an integer, where that integer is equal to 2k squared plus 2k, but who cares? 2k squared plus 2k is also an integer. So n squared is equal to 2 times an integer plus 1. And based on the definition of odd numbers, we have proved that n squared is odd. So we proved the contrapositive of proposition 4.644. So basically we proved that proposition 2 using the method of proof by contraposition. Now I told you before that this method is very similar to the method of proof by contradiction. To show you how similar they are, I'm going to prove the same proposition 4.6.4 using the method of proof by contradiction, so you can see both of them side by side and compare them. So if I want to prove this proposition using contradiction, I have to first assume that this proposition is not correct, right? So if this position is false, if this proposition is false, so there is some integer n such that n squared is even and n is odd, right? So since n is odd, we can say n squared is equal to 2k plus 1 squared, right? Instead of n, I put 2k plus 1 since n is odd. So in this very similar way, I substitute n by its equivalent value, which is 2k plus 1, and I use some basic algebra to reach that n squared is equal to 2 times another integer plus 1. So I will obtain that n squared is odd because it's equal to 2 times an integer plus 1. So here I reach to the conclusion that n squared is odd. However, we said that n squared is even, right? So it's impossible that n squared is both even and odd, because this contradicts with the theorem 4.6.2, which we proved earlier in this section. So we are done with the proof because we reached to contradiction, right? So as you see, the method of proof by contraposition is very similar to the method of proof by contradiction. Okay, so let's see a bit more difficult example. We are going to prove that square root of 2 is irrational, okay? I'm going to use the method of proof by contradiction. So basically the first step is I suppose that square root of 2 is rational, right? So square root of 2 is rational. That's why there are some integers m and n such that a square root of 2 is equal to m divided by n. And I'm going to make another assumption. I assume that m and n has no common factors. So even if they have common factors, we can cancel out their common factors from numerator and denominator. So that's a valid assumption. That's an assumption that doesn't lose the generality of the problem that I'm solving. So as you see, since square root of 2 is m over n, by squaring both sides of this equation, we will obtain 2 is equal to m squared divided by n squared, or equivalently, we can get m squared is equal to 2n squared. And since m squared is 2 times another integer, which is n squared, so m squared is even. And based on the proposition 4.6.4 that I just proved, we can conclude that m is also even, right? So since m is even, based on the definition of even numbers, and m can be written as 2 times k for some integer k, and since m squared was 2 times n squared, I just substitute m with 2k, so m squared, which is equal to 2k squared, which is 4k squared, and 4k squared is equal to 2n squared, because here we had m squared is equal to 2n squared. So by dividing both sides of this equation by 2, we get n squared is equal to 2k squared. Again, n squared is equal to 2k squared. So based on the definition of even numbers, n squared is also even, right? Because n squared is equal to 2 times some other integer, which is k squared. So since n squared is even, based on the proposition 4.6.4, we conclude that n is also even. So n is even and m is even, right? So m and n have a common factor of 2, which contradicts our first assumption that we assume that m and n has no common factors. So we reach to contradiction because it's impossible that m and n both have a common factor and do not have a common factor. So these two contradicts, these two will reach us to a contradiction, and as a result we are done with the proof of theorem 4.7.1 using the method of proof by contradiction. And the last theorem that we are going to prove in chapter 4 is proving that the set of prime numbers is an infinite set. There are infinite number of prime numbers. Let's prove this using the method of contradiction. Let's assume that the set of prime numbers is not infinite, right? So it should be finite. We should have a finite list of prime numbers, and if we sort them in an ascending order, it should look like something like this: 2, 3, 5, 7, 11, all the way to p, where p becomes the largest prime number, right? So I will construct an integer n in the following way. I multiply all the prime numbers together from 2, 3, 5, 7 all the way to p, and then after this long product I add the result by 1. Okay, this is n. This is how I like to define a new integer n. Now we know that n is greater than 1 and n is divisible by some prime number q, right? Because n is obviously not equal to any of these prime numbers. So since 2, 3, 5, 7, 11 all the way to p are the only prime numbers and n is not equal to any of these, so n is not prime, n is composite. And since n is greater than 1, it should be divisible by some prime number, because any composite integer is divisible by some prime number, correct? Otherwise it becomes prime. So it is divisible by some prime number like q, and since q is prime, q should be one of these prime numbers, because as we said, prime numbers are, we assume that prime numbers are finite, so it should be either 2, 3, 5, 7, 11 all the way to p. Should be one of these, right? So basically q divides this product because q is equal to one of them, so q divides this product. And since q divides this product, q does not divide this product plus 1, because if you divide q to such integer, the remainder becomes -1. It's impossible. Q does not divide this product plus 1, right? So this product plus 1 was called n, right? So q does not divide n, but previously we assumed that n is divisible by that q. That's how we define q. So in one sentence we said n is divisible by q And in another sentence we said n is not divisible by q. So these two will reach us to a contradiction, and as a result we conclude that we have proved theorem 4.7.4.